Today, the lecture is about sums of random variables, okay? So we started out talking about one random variable, then we moved on to two random variables. We spent a lot of time there talking about joints and conditionals and marginals and so on. And now we're kind of taking it to the next level, right? Just an arbitrary number of random variables. What can you say about them, right? And so a lot of times this comes up in natural situations where you do a bunch of experiments and you accumulate the results and then you try and reason about the underlying distribution, right? So for example, say that I want to verify whether these dice are fair, right? How would I know? Well, I could just keep on rolling them and I could make this table of sums from 2 to 12, and I could try to check that table against my knowledge about what a fair die should produce, right? Something like this. So today is kind of like about how do you actually do those experiments and how can you reason about the results. And we're going to continue this theme on through next time. So basically the setup is that we have a sequence of random variables. For example, like a series of coin flips or a series of observations about the day's weather or something. And then we want to process these to kind of extract information about, for example, the underlying random process that produced them. For example, the underlying PDF, okay? And so the easiest way to do this is by looking at things like the mean of these random variables or the sum of these random variables. So the easiest way is via either the sum of the random variables, which means that I take each of my random variables and I add them up, which is just like this, sum from I equals 1 to n of xi, or I could take the average of them, which would just be like averaging this sum by dividing it by n, okay? And so each of these in themselves is a random variable, okay? If I add two random variables, I get another random variable. And so most of today's lecture is going to be basically about what is the mean, what is the variance, and what is the PDF of this new random variable that I get by adding things together, okay? So the expected values are easy, right? This is stuff that we've known since the beginning, right? So the expected values are pretty straightforward. So for example, the expected value of the sum, and so far I haven't said anything about, how these random variables are related to each other. I mean, it makes the most sense to think about that these are all coming from the same distribution, like the same roll of the same die. But in general, in the beginning, these could be anything, right? So the expected value of the sum is just going to be the expected value of this, which I know I can take apart as the sum of the expected values, right? And then it follows immediately that the expected value of the mean, and here I'm going to call this guy, sorry, I guess I shouldn't, sorry. I'm going to call this S sub n, and I'm going to call this M sub n, so the sum and the mean of n random variables, right? So expected value of the mean is just going to be 1 over n times the expected value of the sum. So that makes sense, right? The sum of the expected values is the expected value of the sum. The average of the expected values is the expected value of the average. Everything makes sense. So what about the variance, okay? Well, the variance may be a little bit trickier, but we can still figure it out, right? So the variance of the sum is like saying the expected value of the sum squared minus the expected value of the sum squared. And we found this part out already over here, so we have to figure out what is this, right? So what is the expected value of the sum squared? Well, we can expand it out, right? So it's like saying the expected value of the sum times itself. And I can see actually that there are going to be, n squared terms here. If I multiply this out, I'm not going to multiply everything out. So you can kind of see the pattern. Basically, there are going to be n squared terms inside this sum. And that's okay. So if I just kind of bring the expected value through, then what I have is that the expected value of the sum squared is going to be like the expected value. So basically I can say I've got a sum over I equals 1 to n, j equals 1 to n of the expected value of xi, xj, right? So for every pair of random variables, I have one of those pairs inside this big sum, right? And there are n squared of those terms. And these are exactly what we call the covariances, right? Basically, what is the, yes, that's exactly what we call the covariance between xi and xj, right? This is just like the sum of the covariance of xi and xj together. With the reminder that, if I take the covariance of xi with itself, that's like saying the same as the variance, right? We kind of defined that. Or, write this way, xi squared. Actually, okay, hold on, I messed this up. The covariance is what I get after I subtract off the means, right? So actually, scratch this part out. Sorry, I didn't get here yet. Whoops. Exclamation point. Okay, so this is fine. What I wanted to do was actually this over here, right? So I'm coming back to this. Right? So I established just now that this is like the sum of these guys. And then what is this thing squared, right? That's like saying I take this thing and square it, right? So if I take this thing and square it, I'm going to get the same kind of pattern, right? I'm going to get n squared terms where this part here comes from the first part, and then I have an xi expected value of xj, right? That's better. And now I say, okay, this thing is exactly what we called the covariance between xi and xj. Sorry, I messed that up a little bit earlier, but that's okay. Right, so the variance of the sum is the sum of all the possible covariances. And I can see the special case when I have like x1, where I equals 1 and j equals 1, I'd have like expected value of x1 squared minus the expected value of x1 all squared. That's the variance of x1. So basically, n squared minus n of these terms are just like the diagonal terms, and then the diagonal themselves are the variances, right? So that's like saying that if I have, kind of a matrix of the n variables here and the n variables here, this here is like basically the variance of x1. This here is like the covariance of x1, x2, ... the covariance of x1, xn, and so on. All the way down to here. So I have n squared terms in all, and this is sometimes called the covariance matrix, because I take all the covariances I could possibly create and put them together into one big matrix. And the variance of the sum is just what I get if I add up all these numbers, right? So let me just write that again. The variance of the sum is equal to the sum of all the n squared covariances. Okay? So let me pause and ask questions about how I got to this. Okay, so far these are all like just general random variables, right? Now a special case would be what if these variables were uncorrelated, right? So kind of a special situation, which is to say that the covariance of xi and xj would be equal to 0 if I'm not looking at the same value, which is the same as saying the variables are uncorrelated, right? That's what we called uncorrelated last time. Right? What would that mean? Well, that would mean that all of the non-diagonal elements of this big n squared matrix would be 0, right? The only thing I'd be adding up would be the numbers along the diagonal. And so in that case, the variance of the sum is just the sum of the variances. So certainly if they're uncorrelated, then life is easy. And of course we know that if things are independent, that's the same as saying that implies that things are uncorrelated. So this also applies if things are independent, right? So if the variables are all independent, then I just have the sum of the variances. All right, so questions about this? Okay. So now let's think about the kind of natural situation, which is that each of these xi's is coming from the same distribution, right? I'm rolling the same die, I'm observing the same weather at the same time every day. So basically I'm kind of drawing things from the same distribution, right? And we talked about this a little bit earlier as what we called IID, identically and independently distributed. So this is kind of another even more important special case. Which is saying that all the xi are independent and identically distributed. That means that they have the same PDF. And we abbreviate this as IID. So sometimes from now on, you'll see me saying IID, that's what it means. So that is, each xi has the same PDF, which we'll call like little fx, and they're all independent. Okay, so that makes life a lot easier because now I can say, well, the expected value of each of these things is some number, mu, the mean. And that mean is the same for each of the xi's. And the variance is the same for each of the xi's. So that means that the expected value of the sum is the sum of the expected values, which means I basically have n times the mean. The expected value of the mean of the n random variables is 1 over n times this, so I basically get the mean again, and that makes sense. And how about the variances? So the variance of the sum, we just said would be the sum of the variances, since these are all independent, which means I have n times sigma squared. And now what is the variance of the mean? The variance of the mean is going to be 1 over n squared times the variance of the sum, right? Why is that? Because the mean is 1 over n times the sum, and we know that basically the variance of ax is a squared times the variance of x. And so here my a is 1 over n, and so I get this 1 over n squared, and that means that I have 1 over n times this, so I get 1 over n times sigma squared. And that's the part that has some interesting implications, right? This is basically saying if I take the average of a bunch of random variables that are all basically the same distribution, that the mean is the same mean as I have for each of the guys, but the variance of that mean, the variance of the average of the random variables, is getting smaller and smaller. So as n gets bigger, that 1 over n is going to get smaller and smaller, right? And that's really important from a statistical point of view, and that helps a lot for, again, real-world engineering applications. So this is really key. This is kind of key observation, which is that the variance of the average of a bunch of random variables gets smaller as the number of terms in the sum, or terms in the average or sum, doesn't matter, gets larger. And eventually, in a limit, right, if I were to take the limit as n goes to infinity of this variance, that would be equal to 0, right? As n goes to infinity, this goes down to 1 over infinity, which is 0, right? So the intuition here is that I have a bunch of random variables, and again, you can think about these like kind of like noisy observations, right? I'm trying to observe something, and when I observe it, there's some natural noise in it, right? And how can I mitigate the noise? I can take a bunch of observations of the same thing and take the average. What that means is that the noise will be smaller by a factor of n, right? So if I add up n things and take the average, the noise, the variance, is going to be 1 over n as big as it was before, right? Kind of graphically, what that means is that, kind of graphically, this PDF of this mean has to look like, every time I add another random variable, I'm always centered at whatever this thing is. Initially, my PDF of the average looks kind of broad, right? Now, as I start adding more and more observations, the variance gets smaller and smaller. And what this means is that with every new observation, I tighten up this distribution, right? The variance gets less and less. And eventually, what I would expect to happen is that I basically get kind of like a really sharp spike right around the mean, right? Almost like a delta function around the mean. So as n increases, we get a tighter and tighter distribution around the mean. Less and less randomness. Okay, so questions about this? So one thing that we don't exactly know is how fast do we get there, right? So a good question, for example, is, how many times do I have to roll that die to be pretty sure that I am close to the mean of the roll, right? Like how many observations do I need to be within a certain range of the mean? That's kind of the theme of the next part of the lecture, right? So kind of the question is, how fast do we approach the mean? Or approach the value mu, maybe is a better way to think about it. So what I want to do is I want to compare what I want to do is I want to compute this. I want to compute the probability that the mean minus mu is greater than some value epsilon, right? What's the probability that when I take the average of my coin flips that I'm further away from the true mean than epsilon, some number, okay? And this is exactly, again, and I'm just going to be really explicit here, this is the same thing as saying, like, how far is this random variable from its expected value? And this is exactly what we talked about when we defined the Chebyshev inequality, right? This was something from kind of exam 2 material. This is like saying this is exactly what is bounded by Chebyshev. Right? The statement of Chebyshev was something like this. The probability that x minus the expected value of x is greater than some value was bounded by the variance of x over this value squared, okay? And so if I apply that to this problem, right, that's like saying the probability that the mean is further away from its expected value than epsilon is the variance of this thing, which I learned was 1 over n sigma squared over epsilon squared, right? So that's like sigma squared over n epsilon squared. Or I could flip it around and say the probability that I am epsilon close to the mean, right? So here I'm just flipping the sign of this thing, has got to be at least 1 minus this thing. Right, so the probability that the sample mean is far away from the true mean gets smaller and smaller, and the probability that I'm close to the true mean gets bigger and bigger as n increases. And this Chebyshev kind of gives me a bound on how many observations that I need to, how many things I need to see before I can be a certain level of confidence sure that I've got the true mean, okay? So let me just do a kind of a more like a word problem, right? So for example, you know, let's say that, oh no, I became unamplified. The sweater does not have a good grabbing surface. Okay, so for example, let's say that I knew that the variance, the sigma squared, was 5, say, okay? And we want to be 99% sure that the estimate of the mean is within, say, 0.1 of the true mean. Right? So God came down and told me what the variance was, but I don't know what the mean is. All I'm going to do is I'm going to look at the average of these values to see what the mean is, right? And so what I want is that I want to be 99% sure. That's like saying that this number over here has to be at least 99%. I want this probability to be at least 99 over 100, right? And now if I flip it around, that's like saying that, you know, I know sigma, I don't know n, and my epsilon, so this is my sigma squared, this is like my epsilon, so my epsilon squared is 1 over 100, and I want this to be at least, you know, no more than 0.01, just kind of flipping stuff around. So what am I going to get? I'm going to get that n has to be greater than, oops, not 25, this is 5, right? Because I said sigma squared is 5. So n has to be greater than 5 over 1/100th times 1/100th is equal to 50,000, right? So this is saying that without knowing anything else, I need to take at least 50,000 samples to be that sure of getting that close, okay? So questions about this? So I'm going to give you a couple examples of this kind of word problem on the next homework, right? With some more engaging story around it. Okay, so this leads to, I think, 2 key results of today, okay? So, you know, you may have heard of, like, in a colloquial sense, like the law of averages, right? You know, that eventually things have to even out, right? And that's kind of what these results are telling us. So this leads to an important result. The first one is called the weak law of large numbers. Weak, it's weak. Sometimes you may see this abbreviated as WLLN. Not that we're going to do that much. Which says the following. If all my random variables are IID and the expected value is finite, which is always true for the kinds of things that we care about in this class, and for some value of epsilon, the weak law of large numbers says that the limit of the probability mn minus mu is less than epsilon equals 1. So what does this mean? This is saying, okay, suppose I give you epsilon, right? I say, okay, I want you to be within 1/10. No, actually I want you to be within 1/1000th. No, I want you to be within 1/1,000,000th. No matter what epsilon I tell you, basically, as n gets bigger and bigger and bigger, I'm going to be that close to the mean. The probability that my sample average is further away from the mean than that epsilon that I provided, you know, basically the probability that I'm further away from that is 0. The probability that I'm closer than epsilon to the mean is 1. The more and more values I take, eventually I have to get closer and closer and closer. It's just a question of taking n large enough, right? And that's exactly what we proved in some sense with the Chebyshev example, right? Is that Chebyshev tells us an upper bound on how many n we have to take, and as n gets bigger and bigger, certainly eventually I'm going to be within that mean, okay? So let me pause and ask questions about just what this means, what the idea is. Right? So to make it a little more concrete, you know, suppose that, you know, so let's suppose I have a biased coin with the probability of heads being p, and I don't know what p is, okay? So that means the probability of getting tails is 1/p, or 1 minus p. And I guess this is, we're calling heads 1 and tails 0, right? We're talking about this in terms of random variables, right? So if we compute the mean, the weak law of large numbers says that in the limit, the probability that if I were to average my ones and zeros coming from the coin flips, the probability that number would be within epsilon of the true value of p is equal to 1, right? So the average number of successes gets very, very close to p as n gets bigger and bigger. And, you know, Chebyshev gives us a way of bounding exactly how many things we have to take, but we already know from, you know, whenever I ask you to do a Chebyshev example, and then we verify whether the bound is tight or not, right? Most of the time, the bound is not tight, which means that Chebyshev really overestimates the number of samples I need to take. Oftentimes, I'll get to the, you know, right around the mean much faster than Chebyshev would predict, right? So Chebyshev is really conservative. So basically, it's just saying the average number of successes gets arbitrarily close to p as n gets very large. This is like a poor writing, large. And kind of Chebyshev gives some guidance on how fast this happens, but it's often, you know, very conservative, which means that the n that is predicted by Chebyshev is actually usually a lot bigger than you need. Okay, So that's the weak law of large numbers, and the fact that I called it weak must mean that there is another law of large numbers that is strong, right? So what is the strong law of large numbers? So, the strong law. Which we can call like SLN if we wanted to. So here's the setup. Basically, we have, if the xi are IID and the expected value or the mean is finite, and also the variance is finite. We haven't done any examples where these things are not finite. Then the strong law of large numbers says that the probability that in the limit the sample mean is equal to mu is equal to 1. So let's kind of compare the weak law and the strong law. So the difference is kind of subtle, okay? And this is getting a little bit more into the way that mathematicians think about limits and so on, right? But the weak law is just saying that if I tell you a certain tolerance, you're going to get within that tolerance the probability 1. The strong law is saying much more directly that no matter what sequence you manage to come up with, the sample mean is eventually going to be exactly mu as I go to infinity, right? What this is kind of like saying is that any sequence of sample means will eventually, or any sequence of random variables, the sample mean will equal mu with probability 1, right? That means that you can't get some sort of an oddball sequence where I roll the die, and even if the probability of getting each of the numbers is 1/6, I'm never going to get a sequence where I roll the die forever and I get 6 every time. That just is not ever going to happen, right? It basically says that in the limit, as time goes to infinity, eventually the average roll is going to equal to, whatever it is for a fair die, right? 7/2, right? 3.5. So basically, I can't get some sort of weirdo sequence. And this is kind of like exactly what I think gamblers, think about when they think about the law of averages, right? So, in the long run, if you look at all the rolls of the roulette wheel, you're not going to get some day, if everything is fair, where the roulette wheel is rolling black 2/3 and red 1/3. Eventually, it all has to even out, right? So the implication of this is that we can't get some sort of, oddball sequence that never settles to mu. Right? Everything kind of has to average out, Everything eventually averages out. Now, this doesn't necessarily say the rate at which this has to happen, right? So it could take me a very long time to eventually get to the mean, right? I could have some sort of spikes of very weird rolls of the roulette wheel, but if I roll that roulette wheel a zillion times, eventually I'm going to get the right average, okay? Okay, so that's the weak law and the strong law, right? Most of the time, because this is not very, this is like only things that happen in the limit, we usually talk about the weak law in terms of when we're trying to use Chebyshev to think about how many experiments we have to do to be certain within a certain bound of getting a certain result, right? We're going to kind of extend this idea in the next lecture when we talk about things like confidence intervals. So that's going to be something we talk about a little more next time. All right, so comments on this. Okay, so we talked about the expected value of the sum. We talked about the variance of the sum. and the expected value of the mean and the variance of the mean. So the natural next question, right, is I kind of sketched what the PDF of these things had to look like, but can we be more explicit about what the PDF is, right? So if I kind of go back to my picture, if I can find my picture, right? So kind of like this is saying, you know, eventually I know the PDF gets very sharply peaked around the mean, but how do I know exactly what the PDF is, right? Suppose I add two random variables together, what is the PDF, right? I didn't actually derive that yet. And so that's what I'm going to do now, right? So basically, if we return to the sum of the random variables, we talked about the expected value, we talked about the variance, but what is the whole PDF of this thing? Right? It's got to have some sort of PDF. Well, let's proceed from first principles. Okay, let's suppose, first of all, it's surprising that we haven't done this yet, but let's just talk about what is the PDF of adding two random variables together, right? We should be able to do that. So let's start with two random variables. So let's suppose that x and y, and let's suppose that z is equal to x plus y. So what is the PDF of z? Well, this is the kind of thing we could solve. You know, clearly it has to depend on the joint distribution of x and y, right? That's going to be involved somehow. So let's proceed from first principles. You know, remember that I would do this by first finding the CDF and then taking the derivative, right? That's the way we started to do it. We'd say, okay, the CDF of z is the probability that z is less than this value. And that's the probability that x plus y is less than some value. And now I kind of have to sketch, okay, well this is now suddenly something that is in the language of the joint random variable, right? So I can suddenly talk about this in terms of the joint random variable. That's like saying I have x, I have y, and I want to know what is the probability that x plus y is less than z, right? So that's kind of like this kind of region in the xy plane, right? So this is z over here, this is z, this line here is x plus y equals z. So that would mean that I would have to integrate the joint PDF of x and y just over the stripy region, right? So my CDF, well, what's the best way to do this? X goes from 0 to infinity, and then y is going to go from minus infinity up to x, right? So I'm going to basically take, or it's actually up to z minus x, right? So if this value is x, then this number here has to be z minus x, right? So that means I'm integrating from x equals minus to infinity dx. Y is going from minus infinity to the value z minus x dy, and then I integrate the joint PDF here. Okay, so that's the CDF. What is the PDF? The PDF is d dz, the derivative of the CDF, which is, well, you know, here, again, this is like one of these things that is probably a little bit rusty on calculus. This is like what they call the, I think this is the fundamental theorem of calculus. This is like one of the key things where if I'm taking the derivative of this thing with respect to z, all I'm doing is I'm saying, well, this is part of the y integral, and all I do is I plug in, whenever I see y, I plug in this thing. So that's like saying the x part of the integral stays the same, and what I have is this x, and then I have z minus x dx. Okay. Okay, so far, you know, these random variables are just arbitrary random variables, but now here's the clincher. What if x and y are independent, okay? So if x and y are independent, and I take the sum of these things, so
if x and y are independent, that means that the joint PDF decouples into the product of the marginal PDFs, right? So then that would mean that if I sum up these two independent random variables, that the PDF of this thing would be equal to, I'm going to plug in what I know here. This is the part that involves x, and this is the part that involves y. Oh no. You didn't expect it happening in this class, but what has happened? It's a convolution it's a signals thing coming into probability. Oh no. Don't worry, we're not going to talk about this too much, but this is exactly, basically, the convolution of the two PDFs. I'm sorry to ruin your afternoon, but that's what it is, right? So if I want to figure out what is the PDF of the sum, it turns out to be the convolution of the two PDFs. Question mark, exclamation point, right? And even worse than that, so this is something that I decided to kind of cut out of the class, in the past few years, but, this gives you some sort of a crazy sinking feeling in your stomach that actually you could now start to do things like take the Fourier transforms of PDFs, right? Because if I'm convolving things, we already know that convolution in one domain is the same as multiplication in the frequency domain. So if I wanted to compute these PDFs, I could take the Fourier transform of both PDFs, and I could multiply them together in the frequency domain. I could take the inverse Fourier transform. We could do all that, but we're not going to do that. But let me just say this is, hints at the fact that, Fourier transforms can be useful for probability. What? And then, in a way, this is kind of one of, this is a minor reason why signals and probability kind of go together, right? Because you wouldn't know all this stuff about delta functions and convolutions if you hadn't already taken signals, right? And so in a kind of a slangy way, the Fourier transform of a PDF is, what's called a characteristic function, more or less. It's not exactly the Fourier transform, but it's pretty close. And so, if you wanted to read more about this, there is a chunk of the book that talks about characteristic functions. But this is as far as I want to go in terms of talking about this convolution stuff here. This is the main idea, right, is that to get the PDF of the sum, I convolve the individual PDFs, okay? And so what does that mean? That means that if I come back to if I have the sum of a whole bunch of PDFs, and again, these xi's are IID, then kind of what I get is that the Fourier the PDF of this thing, whatever it is basically like the convolution of x, I do that kind of like n times. I convolve the thing against itself over and over again. And so, yes. And then, the mean is basically going to be like this, except I have to normalize by the 1 over n part, right? And so one thing that you can kind of remember from signals, right, is that as I convolve things, I'm not sure how much you did this in signals, kind of like convolving things against themselves over and over again. Eventually, you go from like if you convolve a pulse against itself, you get a triangle. If you convolve the pulse against the triangle again, you get kind of like this cubic thing. And if you convolve it again, you get this quadratic or this quartic thing, right? So the more you convolve something against itself, the eventually sharper it will get, right? Now, just again, this is kind of like an aside, right? So remember that if I convolve a pulse with a pulse, I get a triangle, right? Now that triangle is wider than the pulse, but the 1 over n part, if I were going to look at the average, the 1 over n part will pull that pulse, you know, or pull that triangle more tightly together on the x-axis, right? So it's like we're rescaling the random variable, right? So the more I convolve things, eventually I get something that's smoother and smoother, and I get something that's really peaked around the mean, okay? And to be honest, that kind of hand waving is all I'm going to really say about what happens. But for those of you that are mathematically curious, that's kind of like what's going on, okay? So comments or questions about this? Okay, one final note for today, which is that, you know, so far I've been talking about adding up a number of random variables, right? So basically, we talked about adding up n random variables. And mostly up to this point, we were kind of concerned about n getting bigger and bigger, but what if n itself is random? Right? And actually, this is kind of similar to the problem I just assigned in the homework, which seemed to generate a lot of discussion / confusion, right? The problem that was like Gamefly or Netflix, right? I'm sending you DVDs, and the n, the number of DVDs you get, is a random number, and then I'm looking at the sum of a bunch of xi's, which are the shipping costs. And so actually, we already kind of did this problem as a preview to what I'm saying right now, which is that, you know, the expected value of the sum of these guys, right, is going to be n times the expected value of, well, actually, let me put it this way. So what is the expected value of the sum of n random variables where this is a random variable itself? Well, we just learned last week, was it that long ago, that I can get this thing by doing this kind of double expectation, right? This is like the law of iterated expectation. Right? So here, if I tell you what n is, right, that's kind of what I was doing here and scribbled out. If I tell you what n is, the expected value of the sum is just n times mu, or, you know, n times the expected value of whatever x is, right? And now I take the expectation again, and I take the mu out, and I have basically it's the expected value of n times the expected value of x, right? So for example, let's say that, you know, make this a little more concrete, let's say that xj is the number of cans that you, that the jth person brings to the recycling bin. And let's suppose this is IID, meaning that every person has the same distribution, and we say that that's a Poisson random variable with mean 40, okay? And then let's say that the number of people is a geometric random variable with parameter 1/10, okay? And I want to know what is the expected value of the total number of cans that come to my recycling plant. Well, by what I just said here, that's like saying I take the expected value of each of the x's and the expected value of n. I told you that this was 40 per person, and I expect on the average 10 people, so I get 400, you know, as my number of cans, right? Very easy. And that's the same logic that you were hopefully applying on the last homework, right? Is what is the expected total shipping cost? It's the expected cost of shipping one DVD times the expected number of DVDs that you have to ship, right? just the product of those two things. So, comments or questions about this? Okay, so I feel pretty good about that. So I think that's a good place to stop the lecture. And so next time, before you jumble up, the next thing we're going to talk about is, you know, one final observation about adding up lots of random variables, which is that remembering that Plinko board from Price is Right, that eventually that binomial sum looked like a Gaussian, right? And that's going to be the topic of the next lecture, is why when we add up lots and lots of random variables of the same PDF, why things always end up looking Gaussian. And we're going to come back to Q tables and stuff like that. Okay, so I'll see you on Thursday.